Tonight, we're going to shrink down to a scale so small that it breaks everything you think you know about solid matter. We're going to explore the atomic nucleus. You've probably heard that atoms are mostly empty space, but here's what almost nobody truly grasps. The nucleus, that tiny speck at the center of every atom, is so unbelievably small compared to the atom itself that if you scaled an atom up to the size of a football stadium, the nucleus would be smaller than a single grain of sand sitting at the center of the field. And yet, that grain of sand would contain 99.95% of the entire stadium's mass. Almost everything you are, everything you've ever touched, is concentrated in a space you cannot even begin to imagine. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, or at least something you think you know. Matter is solid. The chair you're sitting on right now feels firm beneath you. The floor holds your weight. The walls of your room stand rigid and unyielding. When you knock on a table, your knuckles meet resistance. There's something there. Something real. Something substantial. Your entire life has been built on this assumption. Solid things are solid. Dense things are heavy. Matter is stuff. And stuff fills space. But here's what physics reveals when you look closely enough. Almost none of that is true. The solidity you feel, the resistance your knuckles meet, the weight of the ground beneath your feet, none of that comes from matter actually filling space. It comes from forces, electromagnetic forces between atoms pushing back against each other. The atoms themselves, the fundamental building blocks of everything you've ever seen or touched, are almost entirely empty. And at the center of each atom, in a region so unimaginably small that calling it tiny doesn't even begin to do it justice, sits the nucleus, a speck so small it defies every analogy we can come up with. And yet that speck contains almost all of the atom's mass. Almost everything that gives you weight, everything that makes matter feel like matter, is concentrated in a space so small that it essentially doesn't exist compared to the atom it sits inside. Tonight, we're going to try to understand just how small that nucleus really is. And I'll warn you now, it's going to challenge your ability to picture things, because the scale we're dealing with here is so extreme that even the best analogies break down eventually. But we're going to try anyway, building up layer by layer until the true scale of the atomic nucleus starts to sink in. Let's begin with the atom itself. An atom is small, you know that. Everyone knows that. But most people don't really appreciate just how small an atom is because we never interact with individual atoms in our daily lives. We interact with trillions upon trillions of them at once, and together they create the illusion of continuous solid matter. A typical atom has a diameter of about 1/10,000,000,000th of a meter. Scientists call this unit an angstrom, and it's written as 10 to the negative 10 meters. That number means nothing to most people, so let's make it concrete. Take a single strand of your hair. A human hair is about 75 micrometers thick, which is 75 millionths of a meter. Now imagine lining up atoms side by side across the width of that hair. You would need roughly 750,000 atoms to span that distance. 750,000 atoms across something as thin as a single hair. That's how small atoms are. If you could somehow magnify a single atom to the size of a marble, about 1 centimeter across, then at that same magnification, the marble itself would be about the size of the Earth. That's the kind of scale difference we're talking about. An atom is to a marble what a marble is to the entire planet. Now, atoms are the building blocks of everything. Every material you've ever encountered, every substance, every surface, every liquid, every gas, all of it is made of atoms. Your body contains roughly 7 billion atoms. That's 7 followed by 27 zeros. Each one of those atoms is unimaginably small on its own, but together they make up you. They form your bones, your blood, your skin, your brain, every cell, and every molecule. For a long time, scientists thought atoms were the smallest things that existed. The word atom comes from the Greek atomos, meaning indivisible. But atoms aren't indivisible. They have internal structure. And that internal structure is where things get truly bizarre. An atom consists of two main regions. There's a cloud of electrons on the outside, and there's a nucleus at the center. The electrons are incredibly light particles that carry negative electric charge. They don't orbit the nucleus in neat circular paths like planets around a sun, despite what many diagrams show. Instead, they exist in fuzzy probability clouds called orbitals, spread out over a relatively large volume. These electron clouds are what define the atom's size. When we say an atom has a diameter of about 1 angstrom, we're really talking about the size of its electron cloud. The space the electrons occupy, or more precisely, the space where you're likely to find them, that's what gives the atom its apparent size. But here's the thing, electrons are tiny. They have almost no mass compared to the rest of the atom. An electron is about 1,836 times lighter than a single proton, and they're spread out over this relatively large volume. The electron cloud is diffuse, wispy, more like a fog than a solid shell. Now, let's turn to the nucleus. The nucleus sits at the exact center of the atom. It contains protons, which carry positive electric charge, and neutrons, which carry no charge at all. Together, protons and neutrons account for almost all of the atom's mass. When you step on a bathroom scale and it reads a number, that number comes almost entirely from the protons and neutrons in the nuclei of your atoms. The electrons contribute almost nothing. Less than 0.05% of your body's mass comes from electrons. The rest, 99.95% and more, comes from the nuclei. So the nucleus is where the mass lives. That alone makes it important. But what makes it truly extraordinary is how small it is compared to the atom it sits inside. A typical atomic nucleus has a diameter of roughly 1 to 10 femtometers. A femtometer is 1 quadrillionth of a meter. That's 10 to the negative 15 meters. Let's compare that to the atom's overall diameter of roughly 1 angstrom, which is 10 to the negative 10 meters. The ratio between the atom size and the nucleus's size is approximately 100,000 to 1. The atom is about 100,000 times wider than its own nucleus. 100,000 to 1. Let that number sit in your mind for a moment, because we're about to explore what it actually means. Let's start with an analogy that gets used a lot because it's genuinely one of the best. Imagine you're standing in the middle of a large football stadium. A professional football stadium is roughly 300 meters across from one end of the stands to the other. Now imagine you place a single grain of sand at the center of the field. Not a baseball, not a marble, a grain of sand. Something about 3 millimeters across, sitting right in the middle of the 50-yard line. You'd struggle to even see it from the stands. In this analogy, the stadium is the atom. The grain of sand is the nucleus. Everything else, the seats, the field, the sky above, the air between you and the marble, All of that space is empty. There's nothing there. Just the grain of sand sitting alone in the middle of an enormous structure. The electron cloud would be a faint haze somewhere out near the upper decks of the stadium, essentially weightless, contributing almost nothing in terms of mass. All the substance, or the weight, or the meaningful matter of this stadium-sized atom is concentrated in that one tiny grain sitting at the center of the field. Now think about what that means for everyday matter. Everything around you right now, the device you're listening to this on, the air in your lungs, the ground beneath the building you're in, all of it is made of atoms. And every single one of those atoms is like that stadium, almost entirely empty, with a tiny dense speck at the center. The solidity you experience, the firmness of your chair, the rigidity of your walls, none of that comes from matter filling space. It comes from electromagnetic forces pushing back against you. Forces generated by the electron clouds of atoms interacting with each other. You are literally sitting on a cushion of electromagnetic force, hovering above empty space. You have never truly touched anything in your life, not in the sense of one piece of matter making contact with another. What you feel as touch is the electromagnetic repulsion between the electron clouds of your atoms and the electron clouds of whatever you're touching. The atoms never actually make contact. Their nuclei never come anywhere close to each other under normal circumstances. They're separated by vast relative distances, each one sitting alone in its own stadium-sized region of empty space. But let's push the analogy further, because the stadium comparison, while powerful, still doesn't fully capture the scale. A stadium is big, but it's something you can stand inside. You can look across it and see the other side. It feels large but manageable. So let's go bigger. Imagine scaling the atom up so that the nucleus is the size of a basketball. A standard basketball has a diameter of about 24 centimeters, roughly 9.5 inches. If the nucleus were the size of a basketball, how big would the atom be? The atom would have a diameter of about 24 kilometers. That's roughly 15 miles. The atom would be large enough to cover a major city. The entire metropolitan area of a city like Manhattan in New York would fit comfortably inside this scaled-up atom. And all the mass, all the weight, everything that matters in terms of substance would be concentrated in that single basketball sitting somewhere near the center of the city. Everything else, every building, every street, every park, the rivers, the bridges, all of it would be empty space in atomic terms, occupied by nothing but a faint electron haze too light to register on any meaningful scale. Let me try one more. Imagine the nucleus is the size of a grain of sand. A small grain of sand is roughly 0.5 millimeter across. If the nucleus were that grain of sand, the atom would be about 50 meters in diameter. That's roughly the size of an Olympic swimming pool, but in all 3 dimensions. A sphere 50 meters across, with one grain of sand floating at its center. That's an atom. Now here's what really starts to break your mind. Remember, this isn't some exotic rare structure that exists only in particle accelerators or theoretical physics. This is everything. Every atom of every element in the universe has this structure. The oxygen you're breathing right now is made of atoms that are almost entirely empty space with tiny nuclei at their centers. The carbon in your body, the iron in your blood, the calcium in your bones, all of it follows the same pattern. Every atom is a vast emptiness with a speck of incredible density at its center. Your body contains roughly 7 billion atoms. Each one is almost entirely empty. If you could somehow remove all the empty space from all the atoms in your body, if you could compress all the nuclei together so they were touching each other with no gaps in between, how much space would your body actually take up? The answer is staggering. All the actual nuclear matter in your body, every proton and every neutron from every atom, would compress down to a volume smaller than a single grain of fine sand. Some estimates put it at a cube roughly 1/500th of a centimeter on each side. That's essentially invisible to the naked eye. Everything that makes you physically you, every kilogram of your body weight, would fit into a speck too small to see. This means that right now, as you sit or stand or lie down, the matter that composes you is overwhelmingly nothing. You are almost entirely empty space, held together by forces. The real substance of your existence, the mass that gives you weight and presence, occupies a volume so small it makes a grain of dust look like a mountain. And this applies to everything. The Earth, with all its mass, all its mountains, all its oceans, every continent, every creature, every rock, every drop of water. If you removed all the empty space from all its atoms, the entire planet would compress down to a sphere roughly the size of a large sports arena. Some calculations suggest it would be about 300 to 400 meters across. That's the Earth. A planet with a diameter of nearly 13,000 kilometers, reduced to something you could walk around in a few minutes, all because atoms are almost entirely empty, and all their mass is concentrated in nuclei that are 100,000 times smaller than the atoms themselves. Let's talk about actual measured sizes now, because the numbers themselves tell a powerful story. The simplest atom is hydrogen. It has one proton as its nucleus and one electron in its cloud. The hydrogen atom has a diameter of about 1.2 angstroms, which is 120 picometers, or 1.2 times 10 to the negative 10 meters. The hydrogen nucleus, which is just a single proton, has a diameter of about 1.7 femtometers, or 1.7 times 10 to the negative 15 meters. The ratio between these two numbers is roughly 70,000 to 1. The hydrogen atom is about 70,000 times wider than its own nucleus. Not quite the 100,000 to 1 ratio I mentioned earlier, but close. The ratio varies slightly depending on the element because different atoms have different sized electron clouds and different sized nuclei. For a larger atom like uranium, the picture changes somewhat, but the basic relationship holds. Uranium has 92 protons and typically 146 neutrons in its nucleus. The uranium nucleus has a diameter of about 15 femtometers. That's larger than hydrogen's nucleus, which makes sense because there are far more protons and neutrons packed in there. But the uranium atom as a whole has a diameter of about 375 picometers. So for uranium, the ratio between atom size and nucleus size is about 25,000 to 1. Still enormous, still an overwhelming amount of empty space. The nucleus is still vanishingly small compared to the atom, even for one of the heaviest naturally occurring elements. Across all the elements, from hydrogen with its single proton nucleus to the heaviest atoms produced in laboratories, the nucleus is always between roughly 10,000 and 100,000 times smaller than the atom. The exact ratio changes, but the fundamental picture remains the same. The nucleus is a tiny, incredibly dense point at the center of a vast cloud of almost nothing. Now let's talk about density, because this is where the nucleus becomes truly mind-bending. If nearly all the mass of an atom is concentrated in its nucleus, and the nucleus is 100,000 times smaller in diameter than the atom, then the nucleus must be extraordinarily dense. And it is the density of nuclear matter is approximately 230 trillion grams per cubic centimeter. Let me read that out. 230 million grams in a single cubic centimeter of nuclear material. That's 2.3 times 10 to the 14 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Iron has a density of about 7.87 grams per cubic centimeter. Lead, which feels impressively heavy when you hold it, has a density of about 11.3 grams per cubic centimeter. Gold is about 19.3 grams per cubic centimeter. Nuclear matter is about 230 trillion times denser than water. It's about 20 trillion times denser than lead. These numbers are so large they essentially lose meaning. There's nothing in everyday experience that's even remotely close to this density. Here's a way to try to make it tangible. Imagine you could take a small cube of pure nuclear matter with no empty space between the nucleons, just protons and neutrons packed as tightly as they are inside an actual nucleus. Imagine this cube is 1 centimeter on each side, about the size of a sugar cube. That sugar cube-sized piece of nuclear matter would weigh approximately 230 million metric tons. 230 million metric tons in something you could hold between your thumb and forefinger. Assuming that you could hold it, which you obviously couldn't because it would weigh more than a mountain. Let me try to put 230 million metric tons in perspective. The Great Pyramid of Giza, one of the largest structures ever built by humans, weighs about 6 million metric tons. A sugar cube of nuclear matter would weigh as much as roughly 38 Great Pyramids. All the water in a moderately sized lake, compressed into something the size of a die you'd roll in a board game. This density is not a theoretical curiosity. It's real. Every nucleus in every atom in your body has this density right now. The protons and neutrons inside the nuclei of your atoms are packed at this insane density, separated from the protons and neutrons in neighboring atoms by the vast relative emptiness of the electron clouds. You are, at this very moment, carrying around specks of matter so dense that a cubic centimeter of the stuff would outweigh mountains. You just don't notice because each individual nucleus is so incredibly small that its mass is tiny in absolute terms. It's only relative to its size that the density becomes mind-boggling. There is one place in the universe where nuclear density exists on a macroscopic scale, and we'll talk about that later. But for now, the important thing to understand is that the nucleus is the densest naturally occurring concentration of matter in ordinary experience. Nothing else comes close. Let's return to the emptiness for a moment because I want to make sure this really sinks in. You might hear that atoms are mostly empty space and think, yes, I know that, and move on. But I want you to actually sit with it, because the implications are staggering. Think about a solid steel beam, something used in construction. It feels completely solid. You can hit it with a hammer and it rings. It supports enormous weight. It's one of the strongest materials we commonly use. That steel beam is made of iron and carbon atoms, along with small amounts of other elements. Every single one of those atoms is mostly empty space. The nuclei of those iron atoms are 100,000 times smaller than the atoms themselves. The steel beam, for all its apparent solidity, is overwhelmingly nothing. If you could see individual atoms, You'd see tiny points of mass floating in vast regions of emptiness, held in position by electromagnetic forces. The same is true for diamond, for concrete, for the ground beneath your feet. The hardest, most unyielding substances you can imagine are almost entirely empty. Space. Their strength comes from the arrangement of electromagnetic forces between atoms, not from matter filling space. This is one of the most profound disconnects in all of science. The world as we experience it, solid, tangible, heavy, full of texture and resistance, bears almost no resemblance to the world as it actually is at the atomic level. At the atomic level, matter is mostly void. The nucleus, the tiny seed of mass at the center of each atom, is the closest thing to substance that actually exists. And it's so small that if you held the entire atom in your hand, you'd need a microscope more powerful than any ever built just to see the nucleus inside it. No such microscope exists, by the way. We've never directly seen a nucleus with visible light. You can't. Visible light has a wavelength of about 400 to 700 nanometers. A nucleus is roughly 1 femtometer across. That's hundreds of millions of times smaller than the shortest wavelength of visible light. Light waves pass right over the nucleus like ocean waves passing over a pebble on the seabed. The nucleus is simply too small to interact with visible light in any meaningful way. To probe the nucleus, physicists use particle accelerators, smashing high-energy particles into atoms and analyzing what comes out. The nucleus reveals itself not through light, but through collisions, through violence, through the debris of impact. This is how Ernest Rutherford first discovered the nucleus in 1911. He and his colleagues Hans Geiger and Ernest Marsden fired a beam of alpha particles, which are essentially helium nuclei, at a thin sheet of gold foil. Most of the alpha particles passed straight through the foil as if nothing were there. This alone was stunning. It meant that gold atoms, despite feeling completely solid as a sheet of metal, were mostly empty space. The alpha particles sailed through the vast emptiness between nuclei without hitting anything. But some alpha particles bounced back. A very small fraction, roughly 1 in 8,000, came back at large angles. Some even bounced almost straight back toward the source. Rutherford later said it was as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. That was the moment the nucleus was discovered. Those rare deflections could only be explained if the positive charge and nearly all the mass of the atom were concentrated in a tiny, incredibly dense point at the center, the nucleus. What Rutherford had found, without fully realizing it at first, was that the atom was almost entirely empty. That the mass everyone assumed was spread throughout the atom was actually crammed into a volume roughly 1 quadrillionth the size of the atom itself. 1 quadrillionth, a million billion times smaller in volume. All the mass sitting in essentially no space at all. And tonight, we're going to go deeper into that speck. We're going to explore what's inside it, how it holds itself together against forces that should tear it apart, and what it means for the universe that all of matter, all of reality as we experience it, is built on foundations so vanishingly small that they exist at the very edge of what the word small can mean. The nucleus is not just small, it's the smallest meaningful structure in ordinary matter. Quarks and electrons may be smaller, or may be point-like with no size at all. But the nucleus is the smallest composite object that makes atoms what they are. It defines which element an atom belongs to. It determines the atom's mass. It decides whether that atom is stable or radioactive. It governs whether atoms can fuse together in the hearts of stars or split apart in nuclear reactors. Everything important about an atom, from a nuclear physics perspective, comes from this tiny central core. And it does all of this from a region of space so small that the atom surrounding it is, by comparison, an ocean of nothing. Think about what this means for you right now, in this moment. Every sensation of weight and solidity you have ever felt comes from trillions upon trillions of nuclei. Each one a speck of staggering density, each one 100,000 times smaller than the atom it inhabits, each one carrying almost all of the mass you can feel. You're built from almost nothing. Tiny seeds of matter floating in emptiness, held together by forces, creating the illusion of solid reality. That illusion is convincing. It has to be. Evolution gave us senses tuned to the macroscopic world, a world where matter seems continuous and solid and real. But beneath that comforting surface, the truth is stranger than anything evolution prepared us for. Almost everything is empty, and the tiny fraction that isn't empty is so incredibly small and so incredibly dense that it exists in a realm beyond anything our senses can reach. That realm is the nucleus. And we're just getting started, so now we know how small the nucleus is. We know it's a speck 100,000 times smaller than the atom it inhabits. We know it contains almost all of the atom's mass compressed into a volume so tiny that it barely exists in any meaningful spatial sense. We know the density of nuclear matter is so extreme that a sugar cube of the stuff would outweigh mountains. But we haven't yet asked the most obvious question. What is the nucleus actually made of? What's inside that speck? What is that impossibly dense little point at the center of every atom? And more importantly, how do the things inside it give rise to the mass, the identity, and the behavior of every element in the periodic table? The answer starts simply enough. The nucleus is made of two types of particles, protons and neutrons. These are the building blocks of every atomic nucleus in the universe. Every nucleus that has ever existed, from the lightest hydrogen atom drifting in interstellar space to the heaviest elements forged in the collapse of dying stars, is built from some combination of protons and neutrons packed together. Protons carry a positive electric charge. Each proton has exactly 1 unit of positive charge, which in physics we define as +1 elementary charge. This charge is fundamental. It's not something the proton acquires or loses under normal conditions. It's built into the proton's identity. A proton without its positive charge wouldn't be a proton anymore. Neutrons carry no electric charge at all. They're electrically neutral, which is where they get their name. They have almost exactly the same mass as protons, just slightly heavier, about 0.14% more massive. For most purposes, you can think of protons and neutrons as being essentially the same mass. They're close enough that the difference rarely matters in everyday nuclear physics. Together, protons and neutrons are called nucleons. They're the constituents of the nucleus, the particles that make it up, and the number of nucleons in a nucleus determines almost everything about how that atom behaves. Let's start with the simplest case. Hydrogen. The most common form of hydrogen has a nucleus made of just 1 proton. That's it. 1 single proton sitting alone. No neutrons. It's the simplest nucleus that exists, and it's also the most abundant type of atom in the universe. About 75% of all the ordinary matter in the cosmos is hydrogen. Most of the atoms in the sun are hydrogen. Most of the atoms in Jupiter are hydrogen. The vast clouds of gas that stretch between stars and galaxies are mostly hydrogen, 1 proton. That's what most of the universe is built from. Now, hydrogen does have heavier versions. Deuterium is a form of hydrogen where the nucleus contains 1 proton and 1 neutron. It's still hydrogen because it still has 1 proton. That's the rule. The number of protons defines the element, but the added neutron makes the nucleus heavier. Deuterium is about twice as massive as ordinary hydrogen. There's also tritium, a form of hydrogen with 1 proton and 2 neutrons. Tritium is radioactive, meaning it's unstable and will eventually decay, but it exists, and it's still hydrogen because it still has 1 proton. These different versions of the same element, same number of protons but different numbers of neutrons, are called isotopes. Every element has isotopes. Some are stable, meaning they last forever. Others are radioactive, meaning they decay over time into other elements. After hydrogen comes helium. The nucleus of the most common form of helium contains 2 protons and 2 neutrons, 4 nucleons in total. Helium is the second most abundant element in the universe, making up about 24% of ordinary matter by mass. It is produced in enormous quantities by nuclear fusion in the cores of stars, where hydrogen nuclei are smashed together to form helium. Every star you see in the night sky is doing this right now, converting hydrogen into helium and releasing energy in the process. Lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen has 8, and so on, all the way through the periodic table. Each element is defined entirely by the number of protons in its nucleus. This number is called the atomic number, and it's the single most important number in chemistry. Carbon is carbon because it has 6 protons. Gold is gold because it has 79 protons. Uranium is uranium because it has 92 protons. Change the number of protons and you change the element entirely. Remove 1 proton from gold and you get platinum. Add 1 proton to gold and you get mercury. The identity of every atom, the thing that determines its chemical properties, how it bonds with other atoms, what kind of materials it forms, all of it is determined by how many protons sit in its nucleus. The number of neutrons matters too, but in a different way. Neutrons don't affect the chemical identity of an atom. A carbon atom with 6 neutrons behaves chemically the same as a carbon atom with 7 neutrons. They bond the same way. They form the same molecules, but the number of neutrons affects the stability of the nucleus. Add too many neutrons or too few, and the nucleus becomes unstable. It becomes radioactive. It will eventually spit out particles or energy or both as it tries to reach a more stable configuration. The total number of protons plus neutrons in a nucleus is called the mass number. This tells you roughly how heavy the nucleus is. Carbon-12 has 6 protons and 6 neutrons for a mass number of 12. Carbon-14, the radioactive isotope used in carbon dating, has 6 protons and 8 neutrons for a mass number of 14. Both are carbon. Both have 6 protons. But carbon-14 is heavier and unstable. As you go up the periodic table, nuclei get larger. They contain more and more protons and neutrons. Oxygen has 8 protons and typically 8 neutrons. Iron has 26 protons and typically 30 neutrons. Gold has 79 protons and 118 neutrons. Uranium has 92 protons and typically 146 neutrons, for a total of 238 nucleons crammed into a single nucleus. And here's what's remarkable. Even uranium, with 238 nucleons, has a nucleus only about 15 femtometers across. That's 15 quadrillionths of a meter. You've packed 238 protons and neutrons into a space about 9 times wider than a single proton. It's like cramming 238 basketballs into a space only 9 basketballs wide. The packing is extraordinarily tight. There's almost no wasted space inside a nucleus. The nucleons are jammed together almost shoulder to shoulder, which is why nuclear matter has such absurd density. But protons and neutrons themselves are not the end of the story. For a long time, physicists thought they were fundamental particles, meaning they had no internal structure. They were thought to be indivisible, the ultimate building blocks. But experiments in the 1950s and 60s started revealing something strange. When physicists fired high-energy particles at protons and neutrons, the results didn't match what you'd expect from hitting a solid, featureless ball. The scattering patterns suggested there was structure inside. Something smaller was in there. In 1964, 2 physicists independently proposed a solution. Murray Gell-Mann at Caltech and George Zweig at CERN both suggested that protons and neutrons were made of even smaller particles. Gell-Mann called them quarks. The name stuck. According to this model, every proton is made of 3 quarks, specifically 2 up quarks and 1 down quark. Every neutron is also made of 3 quarks, but in a different combination. 1 up quark and 2 down quarks, that's it. Just 2 types of quarks, arranged in groups of 3, account for every proton and every neutron in every nucleus of every atom in the universe. Up quarks carry an electric charge of plus 2/3. Down quarks carry a charge of minus 1/3. In a proton, 2 up quarks at plus 2/3 each give plus 4/3, and 1 down quark at minus 1/3 subtracts 1/3, leaving a total charge of plus 1. That's where the proton's positive charge comes from. It's the sum of the charges of its 3 quarks. In a neutron, 1 up quark at plus 2/3 and 2 down quarks at minus 1/3 each give plus 2/3 minus 2/3, which equals 0. That's why the neutron has no electric charge. The quark charges cancel out perfectly. This was confirmed experimentally in the late 1960s and early 1970s at the Stanford Linear Accelerator Center, known as SLAC. Physicists there fired high-energy electrons at protons and observed that the electrons scattered off 3 distinct, point-like objects inside the proton. These experiments, led by Jerome Friedman, Henry Kendall, and Richard Taylor, provided direct evidence that quarks were real physical objects, not just mathematical conveniences. The 3 physicists won the Nobel Prize in Physics in 1990 for this discovery. Now, here's where things get genuinely strange. You might expect that the mass of a proton would simply be the sum of the masses of its 3 quarks. 3 quarks go in, and their combined mass is what the proton weighs. That would make sense. That's how it works with most composite objects. A bag of oranges weighs roughly as much as the oranges inside it. But that's not how it works with protons. Not even close. The mass of an up quark is roughly 2.2 mega electron volts divided by the speed of light squared. The mass of a down quark is roughly 4.7 mega electron volts divided by the speed of light squared. If you add up 2 up quarks and 1 down quark, you get a combined quark mass of roughly 9.1 mega electron volts divided by c squared. The actual measured mass of a proton is 938.3 mega electron volts divided by c squared. The quarks account for only about 1% of the proton's mass. 1%. The other 99% comes from somewhere else entirely. This is one of the most startling facts in all of physics. When you step on a scale, 99% of the number you see doesn't come from the quarks that make up your protons and neutrons. It comes from something else, something invisible, something that has nothing to do with the fundamental particles themselves. So where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the strong force, the force that holds quarks together inside protons and neutrons. The strong force is carried by particles called gluons. Just as photons carry the electromagnetic force and give rise to light and radio waves and all electromagnetic radiation, gluons carry the strong force and bind quarks together. But gluons are very different from photons. Photons are simple. They carry no electric charge. They don't interact with each other. A beam of light can pass through another beam of light without either one being affected. Gluons are not like that at all. Gluons carry what's called color charge, which is the strong force equivalent of electric charge. And because they carry color charge, gluons interact with each other. They don't just connect quarks, they connect to other gluons. This makes the interior of a proton an incredibly complex dynamic environment. Inside a proton, the three quarks are not sitting still. They're in constant violent motion, buzzing around at speeds close to the speed of light, and the space between them isn't empty. It's filled with a seething storm of gluons being exchanged back and forth. Gluons are constantly being created and destroyed. They split into pairs of quarks and antiquarks that pop into existence for the tiniest fraction of a second before annihilating each other and producing more gluons. The interior of a proton is a churning sea of quantum activity. It's one of the most dynamic, energetic environments in nature. All of that activity, all of that frantic exchange of gluons, all of that creation and annihilation of virtual quark pairs, all of it carries energy. And according to Einstein's famous equation E equals mc squared, energy and mass are equivalent. Energy has mass. The kinetic energy of the quarks flying around inside the proton contributes mass. The energy stored in the gluon fields contributes mass. The energy of the virtual quark-antiquark pairs popping in and out of existence contributes mass. When you add it all up, the energy inside the proton accounts for roughly 99% of its mass. The quarks themselves, the actual fundamental particles, contribute almost nothing. The proton's mass is overwhelmingly a product of the strong force's energy, not the quarks it binds together. This means that most of your mass, most of the mass of everything you've ever touched, isn't really coming from particles at all. It's coming from energy. From the frantic activity of gluons and quarks interacting inside every proton and neutron in every nucleus of every atom in your body. You are, quite literally, made mostly of energy. Not in some vague mystical sense, but in a precise, measurable, physical sense. The mass you carry through the world is almost entirely the mass of binding energy frozen into the structure of nucleons by the strong force. The same is true for neutrons. The quarks inside a neutron contribute only about 1% of its mass. The rest is strong force binding energy, just like in the proton. This discovery, which emerged gradually through the development of quantum chromodynamics in the 1970s and has been confirmed by sophisticated computer simulations called lattice QCD, fundamentally changed our understanding of what mass is. Mass isn't simply a property of fundamental particles. Mass is, in large part, a manifestation of energy. The strong force creates mass by confining quarks in a tiny space and generating enormous amounts of energy through the constant exchange of gluons. Now, let's zoom back out slightly and think about what the nucleus looks like when you consider it as a collection of protons and neutrons. A light nucleus, like helium-4, contains just 4 nucleons, 2 protons and 2 neutrons. These are packed together in a roughly spherical arrangement. The nucleus is about 3.5 femtometers across. It's incredibly stable. Helium-4 is one of the most tightly bound nuclei in nature, which is why it's the end product of hydrogen fusion in stars. When 4 hydrogen nuclei fuse into one helium nucleus, the resulting helium nucleus is lighter than the 4 hydrogen nuclei that went into it. That missing mass has been converted into energy according to E equals mc squared. That energy is what makes the sun shine and what powers every star in the universe. A medium-weight nucleus like iron 56 contains 26 protons and 30 neutrons. It's about 9 to 10 femtometers across. Iron 56 is special because it has the highest binding energy per nucleon of any nucleus. This means it's the most tightly bound, the most stable. It sits at the bottom of what physicists call the valley of stability. Why that matters so much, why iron occupies this unique position, and what it means for stars and for the existence of every heavy element in the universe, all of that comes down to the forces at work inside the nucleus. And those forces are extraordinary. A heavy nucleus like uranium-238 contains 92 protons and 146 neutrons. It's about 15 femtometers across. Despite being much larger than helium or iron, in nuclear terms, it's still unimaginably small by any human standard. 15 femtometers is 15 quadrillionths of a meter. You could line up roughly 66 billion uranium nuclei across the width of a single millimeter. But uranium is different from iron in an important way. It's less tightly bound. The protons and neutrons in uranium are not held together as firmly as those in iron. This is because uranium has 92 protons, all positively charged, all pushing against each other with electromagnetic repulsion. The strong force holds them together, but it's a closer contest. The nucleus is on the edge of stability. Give it a nudge, fire a neutron into it at the right energy, and the nucleus can split in two. That's nuclear fission, the process that powers nuclear reactors and nuclear weapons. Inside the nucleus, the arrangement of protons and neutrons isn't random. Nucleons organize themselves into energy levels and shells, somewhat analogous to how electrons organize themselves into orbitals around the atom. This nuclear shell model, developed independently by Maria Goeppert-Meyer and J. Hans D. Jensen in 1949, explained a puzzling observation. Certain numbers of protons or neutrons seem to make nuclei unusually stable. These magic numbers, 2, 8, 20, 28, 50, 82, and 126, correspond to completed nuclear shells. When a shell is full, the nucleus is particularly tightly bound and resistant to decay. Helium-4 is doubly magic. It has 2 protons and 2 neutrons, both magic numbers. That's one reason it's so exceptionally stable. Oxygen-16, with 8 protons and 8 neutrons, is also doubly magic. Lead-208, with 82 protons and 126 neutrons, is the heaviest stable, doubly magic nucleus. It's remarkably stable for such a heavy element, and its stability is entirely due to its nuclear shell structure. But the nucleus isn't a rigid, static arrangement of particles sitting in fixed positions. It's a quantum mechanical system, which means it behaves in ways that defy everyday intuition. Nucleons inside the nucleus don't have precise positions. They exist in probability distributions smeared out over the nuclear volume, much like electrons exist in probability clouds around the atom. The nucleus vibrates and oscillates. It can be excited into higher energy states where it wobbles and deforms. Some excited nuclei take on elongated shapes like a football rather than a basketball. Others develop complex multi-lobed shapes. The nucleus is dynamic, alive with quantum motion, constantly shifting and adjusting. Some nuclei are not spherical at all, even in their ground states. Certain isotopes are naturally deformed, stretched into elongated or flattened shapes by the arrangement of their nucleons. These deformed nuclei can rotate, and this rotation creates characteristic patterns of gamma-ray emissions that physicists can detect and measure. And here's something worth pausing on. All of this complexity, all of this structure, the shells, the shapes, the vibrations, the rotations, all of it is happening in a space about 10 femtometers across. Smaller than a single wavelength of visible light by a factor of roughly 50 million. Everything I just described is happening in a region of space so small that it's fundamentally invisible. We know about it only because we've learned to probe it indirectly, firing particles at nuclei and carefully analyzing what comes back. Let me bring this all together. The nucleus is made of protons and neutrons. The number of protons determines what element the atom is. The number of neutrons affects the stability of the nucleus. Together, the protons and neutrons are packed into a space roughly 100,000 times smaller than the atom, at a density so extreme that a teaspoon of the stuff would weigh over 1 billion tons. But protons and neutrons themselves are not fundamental. Each one is made of 3 quarks bound together by gluons. The quarks contribute only about 1% of the nucleon's mass. The other 99% comes from the energy of the strong force, from the seething storm of gluon exchanges and virtual particle creation happening inside every proton and neutron at every moment. This means that the mass you feel when you hold something heavy, the mass that makes planets orbit stars, the mass that curves space-time and creates gravity, almost all of it is energy. Not matter in the traditional sense, not solid little balls of stuff. Energy, trapped by the strong force in a space so small that it exists at the very limits of what the word space can mean. If you could somehow switch off the strong force, protons and neutrons would cease to exist. Nuclei would vanish, atoms would dissolve, everything material in the universe would simply disappear in an instant. Not because the quarks went away, but because the energy that gave them structure and mass was gone. And all of this, every quark, every gluon, every proton, every neutron, every shell and shape and vibration, all of it happens inside a nucleus that's 100,000 times smaller than the atom it sits in. An atom that's already so small, you'd need 750,000 of them to span the width of a human hair. The next time you look at the periodic table, at that neat grid of elements arranged by atomic number, remember what those numbers really mean. Each number represents a count of protons, and each proton is a furious knot of quarks and gluons, carrying mass that's almost entirely made of energy, packed into a space so small it barely exists. The periodic table isn't just a chart of elements, it's a catalogue of different ways that the strong force can bind quarks together into protons and neutrons, and then bind those protons and neutrons together into nuclei, each configuration creating a different element with different properties. Hydrogen, 1 proton, 1 knot of quarks, the simplest possible nucleus, the fuel of stars. Iron, 26 protons, 30 neutrons, 56 knots of quarks, the most stable nucleus, the endpoint of stellar fusion, the element that accumulates in the hearts of dying stars. Gold, 79 protons, 118 neutrons, 197 knots of quarks, forged in the collision of neutron stars, in events so violent they briefly outshine entire galaxies. Uranium, 92 protons, 146 neutrons, 238 knots of quarks, barely stable, teetering on the edge, ready to split apart if given the slightest push. Each element is a different nuclear architecture, a different arrangement of protons and neutrons, a different balance of forces, and inside each proton and neutron, the same frantic dance of quarks and gluons plays out, generating 99% of the mass through sheer energy. You are made of this. Your bones are calcium and phosphorus. Your blood carries iron. Your DNA is built from carbon, nitrogen, oxygen, hydrogen, and phosphorus. Every one of those atoms has a nucleus, and every one of those nuclei is a dense, dynamic, quantum mechanical system of nucleons. And every one of those nucleons is a storm of quarks and gluons, generating mass from energy in a space smaller than anything you could ever hope to see. But if the nucleus is made of protons packed shoulder to shoulder, all carrying positive electric charge, all repelling each other with enormous electromagnetic force, how does it hold together at all? What keeps those protons from blasting apart? What force is strong enough to overcome the relentless electromagnetic repulsion between dozens or even hundreds of positively charged protons crammed into a space just a few femtometers wide? That question leads us to one of the most powerful forces in nature. And the answer is far stranger and more fascinating than you might expect. Here's the problem. And it's a big one. Inside the nucleus, you have protons. And protons carry positive electric charge. Every single proton in every nucleus in the universe carries the same positive charge. And there's a basic rule in electromagnetism that you probably learned in school. Like charges repel. Positive pushes away from positive. Negative pushes away from negative. Only opposite charges attract. This isn't a suggestion. It's one of the most fundamental laws of physics. Electromagnetic repulsion between like charges is absolute, unwavering, and relentless. It never stops. It never weakens to zero. It operates across any distance, from the width of a galaxy down to the interior of a nucleus. And it gets stronger the closer the charges get to each other. That last part is crucial. The electromagnetic force follows what's called an inverse square law. If you halve the distance between two charged particles, the force between them doesn't just double, it quadruples. Cut the distance to a third, and the force increases 9 times. Push the charges closer and closer together, and the repulsive force climbs rapidly, dramatically, relentlessly. Now, think about what's happening inside a nucleus. Take something like an iron nucleus. 26 protons crammed into a space about 9 femtometers across. 9 quadrillionths of a meter. These protons are practically on top of each other. The distances between them are measured in femtometers, the smallest scale at which composite structures exist in ordinary matter. At these distances, the electromagnetic repulsion between protons is enormous. Every proton is pushing against every other proton with tremendous force, trying to blow the nucleus apart. For a heavy nucleus like uranium, the situation is even more extreme. 92 protons packed into a space about 15 femtometers across. 92 positive charges all screaming at each other to get away, all pushing outward with ferocious electromagnetic force. The total electromagnetic repulsion energy inside a uranium nucleus is staggering. If electromagnetic repulsion were the only force at play, no nucleus with more than one proton could exist. Helium couldn't exist. Carbon couldn't exist. Oxygen couldn't exist. The periodic table would contain exactly one element, hydrogen, because hydrogen is the only element whose nucleus has just one proton, and therefore no electromagnetic repulsion to worry about. Every other element requires multiple protons to coexist in the same tiny space, and without something to counteract the electromagnetic repulsion between those protons, that coexistence is impossible. So something else must be going on. There must be another force at work inside the nucleus, a force strong enough to overwhelm the electromagnetic repulsion between protons and hold the nucleus together despite the relentless outward push of like charges. That force exists, and it's called the strong nuclear force, or more precisely, what holds protons and neutrons together inside the nucleus is the residual strong force, sometimes called the nuclear force. It's related to the fundamental strong force that binds quarks together inside protons and neutrons, but it operates differently at the nuclear scale. Think of it this way. The fundamental strong force is what keeps quarks locked inside protons and neutrons. The residual strong force is what leaks out from those protons and neutrons and acts between them, pulling neighboring nucleons toward each other. The residual strong force is mediated by the exchange of particles called pions. A proton or neutron can emit a pion, which travels the short distance to a neighboring nucleon and is absorbed by it. This exchange creates an attractive force between the two nucleons, pulling them together. It's somewhat analogous to how the electromagnetic force works through the exchange of photons, but pions are very different from photons. Pions have mass. They're about 1/7 the mass of a proton, and because they have mass, they can't travel very far before they have to be reabsorbed. This gives the residual strong force a critical property that distinguishes it from electromagnetism. The residual strong force is incredibly short-ranged. It only operates over distances of about 1 to 3 femtometers. Beyond that, it drops off so rapidly that it essentially ceases to exist. At a distance of just a few femtometers, the nuclear force has already faded to almost nothing. By the time you're 10 femtometers away, it's completely negligible. Contrast this with the electromagnetic force, which technically extends to infinity. Two charged particles on opposite sides of the universe still exert a force on each other. It's incredibly tiny at that distance, effectively zero for any practical purpose, but it never truly disappears. The electromagnetic force weakens with distance following the inverse square law, but never actually reaches zero. The strong nuclear force, by comparison, has a hard cutoff. It only works when nucleons are practically touching each other. It's like a force that only exists within arm's reach. If two nucleons are close enough to almost overlap, the strong force grabs them and holds them together with incredible strength. But if they drift even a few femtometers apart, it lets go entirely. At the distances found inside a nucleus, the strong force is roughly 100 times more powerful than the electromagnetic repulsion between protons. It doesn't just barely win, it dominates. This short range has profound consequences for nuclear structure. It means that inside the nucleus, each nucleon only feels the strong force from its immediate neighbors. The nucleons right next to it, touching it or nearly touching it. It doesn't feel the strong force from nucleons on the other side of the nucleus, because those are too far away. Even in a nucleus as small as uranium, which is only about 15 femtometers across, a proton on one side of the nucleus is too far from a proton on the other side for the strong force to connect them. The electromagnetic force, on the other hand, has no such limitation. Every proton feels the electromagnetic repulsion from every other proton in the nucleus, regardless of how far apart they are within the nuclear volume. A proton on one side of a uranium nucleus is being pushed away by all 91 other protons, including the ones on the far side. The electromagnetic force doesn't care about distance within the nucleus. It reaches across the entire nuclear volume. This creates a tug of war, and it's a tug of war with very different rules for each side. The strong force pulls each nucleon toward its nearest neighbors. It's powerful, but it can only reach the nucleons right next to it. The electromagnetic force pushes every proton away from every other proton, and it can reach all of them simultaneously, no matter where they are in the nucleus. Imagine a crowd of people in a room. Each person can grab and hold on to the 2 or 3 people immediately next to them. That's the strong force. Now imagine that every person is also pushing away every other person in the room, even the ones across the room they can't reach with their hands. That's electromagnetic repulsion. When the room is small and there are only a few people, the grabbing wins. Everyone holds on and the group stays together. But as you add more and more people, the cumulative pushing from all sides starts to overwhelm the local grabbing. People on the edges start getting pushed away faster than their neighbors can hold on to them. For small nuclei, the strong force wins easily. In a helium nucleus with just 2 protons and 2 neutrons, every nucleon is basically touching every other nucleon. The strong force acts between all of them simultaneously, and the electromagnetic repulsion between just 2 protons is easily overcome. The nucleus is rock solid, incredibly tightly bound, extremely stable. As nuclei get larger, the balance starts to shift. More protons means more electromagnetic repulsion. And because the electromagnetic force is long-ranged, each new proton added to the nucleus feels the repulsion from all the other protons already in there. But the strong force is short-ranged, so each new nucleon only benefits from the strong force attraction of its immediate neighbors. The strong force contribution grows roughly in proportion to the number of nucleons, because each one gains a few neighbors. But the electromagnetic repulsion grows faster because it depends on the total number of proton pairs, and the number of pairs grows as the square of the number of protons. This is why heavy nuclei become increasingly unstable. The electromagnetic repulsion keeps piling up, proton after proton, each one repelling every other proton across the entire nucleus. But the strong force only holds on locally, each nucleon clinging to its immediate neighbors but unable to reach across to the far side of the nucleus. Eventually, for the very heaviest nuclei, the electromagnetic repulsion nearly wins. The nucleus becomes fragile, teetering on the edge of breaking apart. Neutrons play a crucial role in this balancing act. Neutrons contribute to the strong force because the residual strong force acts between all nucleons, proton-proton, proton-neutron, and neutron-neutron alike. But neutrons don't contribute to electromagnetic repulsion because they have no electric charge. So adding neutrons to a nucleus adds more strong force glue without adding any electromagnetic repulsion. Neutrons are essentially nuclear cement. They help hold the nucleus together without making the electromagnetic problem worse. This is why heavier elements need more neutrons relative to protons. Hydrogen needs no neutrons. Helium does fine with an equal number, 2 protons and 2 neutrons. Carbon has 6 of each, but by the time you get to iron, you need 30 neutrons for 26 protons. The ratio has shifted from 1:1 to about 1.15 to 1. For gold, it's 118 neutrons to 79 protons, a ratio of about 1.49 to 1. For uranium, it's 146 neutrons to 92 protons, a ratio of about 1.59 to 1. The heavier the element, the more neutrons are needed to provide enough strong force glue to counteract the growing electromagnetic repulsion among all those protons. But even neutrons can't keep the nucleus together forever. Beyond a certain size, no amount of neutron glue is enough. The electromagnetic repulsion becomes too great. This is why there are no stable elements beyond lead, which has 82 protons. Bismuth, with 83 protons, was long thought to be stable, but in 2003, physicists demonstrated that bismuth 209 is actually radioactive. It decays with a half-life of about 1.9 times 10 to the 19 years, which is more than 1 billion times the current age of the universe. So, for all practical purposes, bismuth is stable. You'd never notice it decaying. But technically, it does decay. The electromagnetic repulsion eventually wins, even if it takes an unimaginably long time. Every element heavier than bismuth is unambiguously radioactive. Polonium, radon, radium, thorium, uranium, plutonium, all of them decay. The nuclei are too large and contain too many protons for the strong force to hold them together permanently. Given enough time, they will break apart. This brings us to the concept of binding energy, which is central to understanding why some nuclei are stable and others aren't. Binding energy is the energy that holds the nucleus together. More precisely, it's the energy you would need to supply to completely disassemble a nucleus into individual, separated protons and neutrons. The higher the binding energy, the more tightly the nucleus is held together, and the more stable it is. But the number that really matters isn't the total binding energy. It's the binding energy per nucleon. This tells you how tightly bound, on average, each proton or neutron is within the nucleus. And when you plot the binding energy per nucleon against the mass number for all known nuclei, you get one of the most important graphs in all of nuclear physics. The curve starts low for hydrogen, which has essentially 0 binding energy because there's only one nucleon and nothing to bind it to. It rises sharply for the lighter elements as you add nucleons, and the strong force creates increasingly tight binding. Helium-4 has an unusually high binding energy per nucleon for its size, which is why it's so stable. The curve continues to rise through lithium, beryllium, boron, carbon, nitrogen, oxygen, climbing as nuclei get larger, and the strong force binds more and more nucleons together. The curve reaches its peak at iron 56 and nickel 62. These nuclei have the highest binding energy per nucleon of any nuclei in nature, about 8.8 megaelectron volts per nucleon. This means that the nucleons in iron and nickel are more tightly bound than the nucleons in any other element. Iron and nickel sit at the bottom of what physicists call the valley of stability. They are the most energetically favorable nuclear configurations possible. After iron and nickel, the curve starts to decline, slowly at first, then more noticeably. As nuclei get heavier, the binding energy per nucleon decreases. Tin is slightly less tightly bound per nucleon than iron. Gold is less tightly bound than tin. Uranium is less tightly bound still. This decline happens because the electromagnetic repulsion between protons keeps growing with each proton added, while the strong force contribution per nucleon doesn't increase as fast. The balance tips, and heavier nuclei become less and less tightly bound. This curve explains both nuclear fusion and nuclear fission, the two processes by which nuclear energy can be released. Fusion is the process of combining light nuclei into heavier ones. When you take two light nuclei, say two isotopes of hydrogen, and fuse them into helium, the resulting helium nucleus has a higher binding energy per nucleon than the original hydrogen nuclei. The nucleons are more tightly bound in the product than in the reactants. That difference in binding energy is released as kinetic energy, as radiation, as heat. It's the energy that powers stars. Every star in the universe, from red dwarfs that burn for trillions of years to blue supergiants that blaze through their fuel in a few million years, is powered by the fusion of light nuclei into heavier ones moving up the binding energy curve toward iron. Fission is the opposite process. You take a heavy nucleus, like uranium-235, and split it into two lighter nuclei. Those lighter nuclei have higher binding energy per nucleon than the original uranium. Again, the difference in binding energy is released as energy. This is the process that powers nuclear reactors and nuclear weapons. When a uranium-235 nucleus absorbs a slow-moving neutron, it becomes uranium-236, which is highly unstable. The nucleus deforms, stretching into an elongated shape like a peanut. The electromagnetic repulsion between the protons in each half of the peanut pushes the two halves apart while the strong force struggles to hold them together across the narrowing neck in the middle. Within about 10 to the negative 20 seconds, an almost incomprehensibly short time, the neck snaps. The nucleus splits into two mid-weight fragments, typically something like barium and krypton or strontium and xenon, along with 2 or 3 free neutrons. The products are more tightly bound than the original uranium, and the excess energy is released as kinetic energy of the fragments and as radiation. Those freed neutrons can then strike other uranium nuclei, causing them to split as well, releasing more neutrons, which cause more fissions. This is a chain reaction. Controlled, it powers a nuclear reactor. Uncontrolled, it produces a nuclear explosion. Both fusion and fission release energy because both processes move nuclei toward iron, toward the peak of the binding energy curve, toward the valley of stability. Fusion moves light nuclei up toward iron. Fission moves heavy nuclei down toward iron. Iron is the destination, the equilibrium point, the most stable configuration nuclear matter can achieve. This is why iron is so cosmically significant. It's the element where nuclear energy runs out. A star can fuse hydrogen into helium and release energy. It can fuse helium into carbon and release energy. It can continue fusing heavier and heavier elements. Oxygen, neon, silicon, each step releasing energy and keeping the star alive. But when the core becomes iron, fusion stops releasing energy. Fusing iron into anything heavier would require energy input rather than producing energy output. The the star has climbed to the top of the binding energy curve and can go no further. For massive stars, this moment is catastrophic. The iron core can no longer generate the energy needed to support the star's outer layers against gravitational collapse. Within seconds, the core collapses. The outer layers come crashing down. The result is a supernova, one of the most violent explosions in the universe, briefly outshining an entire galaxy. In that explosion, temperatures and pressures become so extreme that elements heavier than iron are forged through neutron capture and other processes that require energy input rather than releasing it. Now, when the balance between the strong force and electromagnetic repulsion fails in a heavy nucleus, the result is radioactive decay. The nucleus transforms itself, releasing particles or energy or both as it seeks a more stable configuration. There are several types of radioactive decay, and each one reveals something about the forces at work inside the nucleus. In alpha decay, the nucleus ejects an alpha particle, which is a cluster of 2 protons and 2 neutrons, essentially a helium-4 nucleus. This is a common decay mode for very heavy nuclei because the alpha particle is so tightly bound that it exists as a coherent unit inside the nucleus. The heavy nucleus essentially sheds a chunk of itself, reducing its proton count by 2 and its mass number by 4, moving down the periodic table toward greater stability. Uranium 238 undergoes alpha decay, emitting an alpha particle and transforming into thorium 234. But here's something genuinely strange about alpha decay. The alpha particle doesn't actually have enough energy to climb over the Coulomb barrier. The wall of electromagnetic repulsion between the escaping alpha particle and the rest of the nucleus. Classically, it should be trapped inside the nucleus forever. It escapes through a quantum mechanical phenomenon called quantum tunneling. The alpha particle has a small but non-zero probability of simply appearing outside the nucleus without ever having crossed the barrier in between. It's as if you threw a ball at a wall and instead of bouncing back, the ball simply appeared on the other side. In quantum mechanics, this is possible. In fact, it's the only reason alpha decay occurs at all. Without quantum tunneling, heavy nuclei like uranium would be stable forever. The probability of tunneling is very small for any given moment, which is why uranium has a half-life of billions of years rather than seconds. The alpha particle tries to escape billions of times per second, bouncing against the nuclear barrier at extraordinary speed, and almost always it fails. But given enough time, it eventually succeeds. In beta decay, a neutron inside the nucleus transforms into a proton, or a proton transforms into a neutron. When a neutron becomes a proton, the nucleus emits an electron and an antineutrino. When a proton becomes a neutron, the nucleus emits a positron and a neutrino. Beta decay changes the balance of protons and neutrons in the nucleus, adjusting the ratio toward the optimal value for that mass number. It's the nucleus fine-tuning its composition, swapping neutrons for protons or vice versa, until it reaches a more stable configuration. In gamma decay, the nucleus doesn't change its composition at all. Instead, it releases energy in the form of a high-energy photon, called a gamma ray. This happens when the nucleus is in an excited state and drops down to a lower energy state, much like an electron dropping between orbitals but at far higher energies. All of these decay processes are driven by the same underlying principle. The nucleus is seeking stability. It's trying to find the configuration with the highest binding energy per nucleon, the deepest point in the valley of stability. Some nuclei are already there. They're stable. They'll exist forever unless something external disrupts them. Others are not quite at the bottom. They're on the slopes of the valley, and they will decay, rolling downhill towards stability, emitting particles and radiation along the way. The rate at which a radioactive nucleus decays is described by its half-life. This is the time it takes for half the nuclei in a sample to decay. Half-lives vary enormously. Some nuclei have half-lives of fractions of a second. Others have half-lives of billions of years. Uranium-238 has a half-life of about 4.5 billion years, roughly the age of the Earth. This is why uranium still exists on Earth. It was created billions of years ago in supernovae and neutron star collisions, and it hasn't had time to fully decay yet. Give it another 4.5 billion years, and half of the remaining uranium will be gone, transformed into thorium and eventually into lead through a long chain of successive decays. At the extreme end, some artificially created nuclei have half-lives measured in microseconds or even nanoseconds. These nuclei are so far from stability that they disintegrate almost as soon as they're formed. The heaviest nucleus ever created belongs to element 118, oganesson, first synthesized in 2002 at the Joint Institute for Nuclear Research in Dubna, Russia. Only a few atoms of it have ever been produced, and they decayed within milliseconds. The electromagnetic repulsion among 118 protons is so overwhelming that no amount of neutrons can stabilize it for long. But there's an intriguing prediction. Some nuclear physicists believe that beyond the known elements, there might be an island of stability, a region of the periodic table where certain combinations of protons and neutrons create nuclei that are unexpectedly long-lived. These would be nuclei near magic numbers, particularly around 114 protons and 184 neutrons, where completed nuclear shells might provide enough extra binding to partially counteract the electromagnetic repulsion. If such nuclei exist and are stable enough to be studied, they could reveal new physics about the strong force and nuclear structure. So far, we haven't reached these hypothetical islands of stability, but the search continues. The interplay between the strong force and electromagnetic repulsion is one of the great balancing acts in nature. Without the strong force, no nucleus beyond hydrogen could exist. Without electromagnetic repulsion, nuclei could grow to any size without limit. Every element heavier than hydrogen exists because the strong force is powerful enough to overcome electromagnetic repulsion at short range. Every element beyond lead is unstable because the electromagnetic repulsion eventually overwhelms the strong force as nuclei grow larger. The entire periodic table is a map of this battle, a record of where the strong force wins, where it barely holds on, and where it finally loses. And all of this plays out in a space smaller than anything you could ever see. A space measured in femtometers. A space 100,000 times smaller than the atom it sits inside. The drama of the nucleus is invisible, silent, and happening everywhere. In every atom of your body, in every star in the sky, in every grain of sand beneath your feet. The strong force and electromagnetic repulsion have been locked in this contest since the first nuclei formed in the minutes after the Big Bang. And they'll continue their quiet struggle for as long as matter exists. So now we understand the nucleus. We know how small it is. We know what it's made of. We know what holds it together and what tries to tear it apart. But there's a bigger question waiting. A question that connects this impossibly tiny speck of matter to the largest. Structures in the universe. What does the nucleus have to do with everything else? Why should you care about a structure so small you could never see it, never touch it, never directly experience it in any way? The answer is that the nucleus is responsible for almost everything you see when you look at the night sky. Every star that has ever burned, every element heavier than hydrogen that has ever existed, every planet that has ever formed, every living thing that has ever drawn breath, all of it traces back to what happens inside atomic nuclei. The nucleus isn't just a detail of physics, it's the engine that drives the universe. Let's start with stars, because stars are, at their core, nuclear machines. Every star you've ever seen, from the faintest red dwarf to the brightest blue supergiant, is powered by nuclear fusion. Fusion is what happens when two light nuclei are pushed together hard enough to overcome the electromagnetic repulsion between their protons and merge into a single heavier nucleus. When this happens, the resulting nucleus has a higher binding energy per nucleon than the original nuclei. That difference in binding energy is released as kinetic energy and radiation. That released energy is what makes stars shine. The sun, the star that makes life on Earth possible, converts about 600 million tons of hydrogen into helium every single second. Every second. 600 million tons of hydrogen nuclei, which are just individual protons, are fused together into helium nuclei, which are clusters of 2 protons and 2 neutrons. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. That missing mass, about 0.7% of the original mass, has been converted into energy according to Einstein's equation, E equals mc squared. 0.7% doesn't sound like much, but when you're converting 600 million tons per second, even a tiny fraction of the mass produces an enormous amount of energy. The sun's total energy output is about 3.8 times 10 to the 26 watts. That's 380 trillion watts. Every second, the sun releases more energy than all of human civilization has produced in its entire history. And all of that energy comes from the nucleus, from the difference in binding energy between hydrogen nuclei and helium nuclei, from the fact that 4 protons bound together as helium are held more tightly than 4 separate protons. The sun is powered by nuclear architecture. This process, hydrogen fusion, is the first stage of stellar nucleosynthesis, the creation of new elements inside stars. And it's the simplest step. Stars don't stop at helium. Depending on their mass, they can continue fusing heavier and heavier elements, climbing the binding energy curve step by step. A star like our sun will spend about 10 billion years fusing hydrogen into helium in its core. That's the main sequence, lifetime. The long, stable middle age of a star's life. During this time, the outward pressure from fusion energy perfectly balances the inward pull of gravity, and the star maintains a steady size and brightness for billions of years. Our sun is about 4.6 billion years into this phase. It has roughly another 5 billion years of hydrogen fusion ahead of it. When the hydrogen in the core runs out, the core contracts and heats up. The outer layers of the star expand enormously, turning the star into a red giant hundreds of times its original size. Eventually, the core gets hot enough to start fusing helium into carbon through a process called the triple alpha process. 3 helium nuclei, each with 2 protons and 2 neutrons, are combined to form a carbon nucleus with 6 protons and 6 neutrons. This requires temperatures of about 100 million degrees Celsius, because the electromagnetic repulsion between helium nuclei is stronger than between hydrogen nuclei. You need far more energy to force them together. The triple alpha process also produces some oxygen when a carbon nucleus captures an additional helium nucleus. The ratio of carbon to oxygen produced in this stage has enormous consequences for the universe. If slightly more carbon is produced, planets end up carbon-rich. If slightly more oxygen is produced, you get water-rich worlds. The balance depends on the precise details of nuclear binding energy, on the exact energy levels within the carbon and oxygen nuclei. The existence of life on Earth may depend on the specific nuclear properties of carbon-12, a nucleus just 6 femtometers across. This particular energy level is called the Hoyle state, predicted by astronomer Fred Hoyle in 1954, before it was experimentally confirmed. Stars like the Sun can fuse helium into carbon, but go no further. Their cores never get hot enough to fuse carbon into anything heavier. When the helium fuel runs out, the star sheds its outer layers as a planetary nebula, and the core remains as a white dwarf, a dense remnant about the size of Earth, but containing roughly half the mass of the Sun. But more massive stars several times heavier than the Sun, can go much further. After fusing helium into carbon, a massive star's core contracts further and heats up even more. At about 600 million degrees, carbon nuclei begin to fuse into neon, sodium, and magnesium. At about 1.5 billion degrees, neon fuses into oxygen and magnesia. At about 2 billion degrees, oxygen fuses into silicon, sulfur, and phosphorus. At about 3 billion degrees, silicon fuses into iron and nickel. Each stage happens faster than the last because each successive fusion reaction releases less energy per nucleon. The star is climbing the binding energy curve, and the curve is flattening out as it approaches the peak at iron. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, perhaps 600 years fusing carbon, about a year fusing neon, 6 months fusing oxygen, and just one single day fusing silicon into iron. One day. After millions of years of steady burning, the final stage of nuclear fusion in a massive star lasts about 24 hours. And then it's over. The core is iron. Iron sits at the peak of the binding energy curve. Fusing iron into anything heavier doesn't release energy. It consumes energy. The star has reached the end of the nuclear road. There is no more fuel that can sustain it. What happens next takes about 1/4 second. Without fusion energy to support it, the iron core collapses under its own gravity. The core falls inward at speeds up to 70,000 kilometers per second, roughly 1/4 the speed of light. In that fraction of a second, the core compresses from something the size of Earth to something the size of a city. The density reaches nuclear density, the density of nuclear matter itself. At that point, the strong force between nucleons suddenly resists further compression. The core rebounds like a compressed spring, sending a shockwave outward through the falling outer layers of the star. The result is a supernova, an explosion so powerful it briefly outshines the combined light of every other star in the galaxy. The energy released in a supernova is about 10 to the 46 joules. That's more energy than the Sun will produce in its entire 10 billion year lifetime, released in a matter of seconds. And in that explosion, something remarkable happens. The temperatures and pressures become so extreme that nuclear reactions occur that could never happen inside a stable star. Neutrons flood the environment in unimaginable densities. Nuclei capture these neutrons rapidly, one after another, building up heavier and heavier elements faster than they can decay. This is called the rapid neutron capture process, or R process. Through the R process, elements heavier than iron are forged. Cobalt, copper, zinc, silver, tin, iodine, barium, gold, platinum, lead, thorium, uranium. All the heavy elements that the star's normal fusion process couldn't create are built in these final violent seconds. But supernovae aren't the only factories for heavy elements. In 2017, astronomers observed something extraordinary. 2 neutron stars spiraling into each other and merging in a cataclysmic collision. The event, called GW170817, was detected first through gravitational waves by the LIGO and Virgo observatories, and then observed across the electromagnetic spectrum by telescopes around the world. The merger produced a kilonova, a burst of light powered by the radioactive decay of freshly synthesized heavy elements. Analysis of the light showed unmistakable signatures of heavy elements being created in real time, including elements like strontium. Astronomers estimated that this single neutron star merger produced several Earth masses worth of gold and platinum. Think about what that means. The gold in any ring you might wear, the platinum in a catalytic converter, the uranium that powers nuclear reactors, none of these elements were made gently. All of these atoms were forged either in the death throes of massive stars or in the collision of neutron stars. They were created in the most violent events the universe has to offer. Scattered into space as debris, eventually incorporated into clouds of gas and dust that collapse to form new stars and planets. Every heavy atom on Earth traveled through space for millions or billions of years before ending up here. The atoms in your body pass through at least one star that lived and died before our solar system formed. Some pass through several. The universe recycled itself to build you. You are, in the most literal physical sense, made of stardust. Not as a metaphor, not as poetry, as measured, verified nuclear physics. The nuclei in your body were assembled inside stars through nuclear fusion and scattered across space when those stars died. You exist because nuclear binding energy made it possible for simple hydrogen to become every element on the periodic table. Now, let me take you somewhere that connects the nucleus to something you can actually observe in the universe. Because there's one place where nuclear density, that absurd density we talked about earlier, exists not in a femtometer scale speck, but on a macroscopic scale. That place is a neutron star. A neutron star is what remains after a massive star explodes as a supernova. The core that collapses during the explosion doesn't always form a black hole. If the core's mass is between about 1.4 and roughly 2 solar masses, it becomes a neutron star. During the collapse, the protons and electrons in the core are crushed together by gravity so intense that they merge, forming neutrons. The entire core becomes a ball of neutrons packed at nuclear density. A neutron star is essentially a giant atomic nucleus, but instead of being a few femtometers across, it's about 20 kilometers across. Instead of containing a few hundred nucleons, it contains roughly 10 to the 57 nucleons. That's a number so vast that writing it out would take 57 digits. The density of a neutron star is approximately the same as the density of an atomic nucleus, about 230 trillion grams per cubic centimeter. Remember that sugar cube analogy from earlier? A sugar cube of nuclear matter would weigh about 230 million metric tons. On a neutron star, that's just what matter is like. Everywhere. The entire object, 20 kilometers across, is at that density. A teaspoon of neutron star material brought to Earth would weigh roughly 1 billion metric tons. It would weigh more than every building in every city on Earth combined. It would be heavier than Mount Everest. All in a volume you could hold in a spoon. If you had a spoon, that could bear the weight, which you obviously don't. Neutron stars spin incredibly fast. When the core of the massive star collapses from Earth-sized down to city-sized, conservation of angular momentum causes it to speed up dramatically. The same principle that makes an ice skater spin faster when she pulls her arms in. Some neutron stars spin hundreds of times per second. The fastest known neutron star, PSRJ 1748-2446 AD, rotates 716 times per second. The surface of this neutron star is moving at roughly 15% the speed of light. If you stood on the surface, which you couldn't because the gravity would crush you into a film of atoms thinner than a sheet of paper, you would be whipped around the entire circumference of the star in about 1.4 milliseconds. The gravity at the surface of a neutron star is about 200 billion times stronger than gravity at Earth's surface. If you dropped an object from a height of 1 meter above a neutron star's surface, it would hit the surface traveling at about 7 million kilometers per hour. For comparison, a bullet from a rifle travels at roughly 3,200 kilometers per hour. The falling object would hit the neutron star at about 2,000 times the speed of a bullet, all from a drop of just 1 meter. The gravitational pull is so extreme that it warps space-time measurably. Light passing near a neutron star bends so much that you could actually see parts of the backside of the star while looking at the front. The star curves space so severely around itself that light wraps partially around it. A person who weighs 70 kilograms on Earth would weigh about 14 trillion kilograms on a neutron star's surface. Neutron stars are the universe showing us what nuclear density looks like at a scale we can observe. Every atomic nucleus has the same density, but each one is too small to study directly with our senses. Neutron stars blow the nucleus up to city size. When astronomers study neutron stars, they're learning about nuclear physics at scales that no laboratory on Earth can replicate. Now let's step back and think about what the nucleus means for the existence of the material world. The periodic table contains about 92 naturally occurring elements, from hydrogen with 1 proton up to uranium with 92. A few heavier elements exist in trace amounts produced by radioactive decay, but for practical purposes, 92 elements is what nature provides. Everything around you, everything on Earth, everything in the solar system, everything in the universe is made from these 92 elements in various combinations. Water is hydrogen and oxygen. Rocks are silicon, oxygen, aluminum, iron, and others. Air is nitrogen and oxygen with traces of argon and carbon dioxide. Your body is carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus, and dozens of trace elements. The properties of every one of these elements are determined by the nucleus. The number of protons in the nucleus defines which element it is. The number of neutrons determines which isotope. The binding energy of the nucleus determines whether it's stable or radioactive. The size and charge of the nucleus determine how the electron cloud arranges itself around it, which in turn determines the atom's chemical properties, how it bonds with other atoms, what molecules it can form, what materials it can create. Chemistry is at its deepest level, a consequence of nuclear physics. The reason carbon can form 4 bonds and create the complex molecules of life, the reason oxygen is reactive and nitrogen is relatively inert, the reason metals conduct electricity and insulators don't, all of these properties ultimately trace back to the number of protons in the nucleus and the electromagnetic field that nucleus creates around itself. Without the nucleus, there is no chemistry. Without chemistry, there are no molecules. Without molecules, there are no materials, no liquids, no gases, no solids, no rocks, no water, no air, no life. Everything that exists in the material world is downstream of the nucleus. It all flows from that femtometer scale structure at the center of every atom. And the abundance of elements in the universe, the reason some elements are common and others are rare, that's determined by nuclear physics too. Hydrogen is the most abundant element because it's the simplest, 1 proton, and it was created in enormous quantities in the Big Bang. Helium is the second most abundant because it's the product of hydrogen fusion in stars, which has been happening for over 13 billion years across hundreds of billions of galaxies. Carbon, nitrogen, and oxygen are common because they're produced in the normal fusion processes of massive stars and distributed by supernovae. Iron is relatively common because it's the endpoint of stellar fusion, the element that accumulates in stellar cores. But gold is rare, platinum is rare, uranium is rare. These elements require the extreme conditions of supernovae or neutron star mergers to form. Those events are violent and brief, producing relatively small amounts of heavy elements compared to the vast quantities of hydrogen and helium that dominate the universe. The rarity of gold isn't arbitrary. It's a direct consequence of nuclear binding energy. Building a nucleus with 79 protons requires conditions that occur only in the most catastrophic events in the cosmos. The entire material composition of the universe is dictated by the properties of the nucleus. Let me bring everything together now. We start this journey with a question about scale. How small is the atomic nucleus? And the answer we found is that it's almost incomprehensibly small. 100,000 times smaller than the atom in diameter. A speck so tiny that if you expanded the atom to the size of a football stadium, the nucleus would be a grain of sand at the center of the field. And yet that grain of sand contains 99.95% of the atom's mass. Inside that speck, protons and neutrons are packed at extraordinary density, each one a composite storm of quarks and gluons, where 99% of the mass comes from binding energy, not from the quarks themselves. The number of protons defines the element. The balance with neutrons determines stability. The binding energy curve determines which reactions power stars and which elements are forged in their deaths. The nucleus is where stars get their energy, where elements get their identity, and where matter gets its mass. There's something humbling about this. You walk through the world feeling solid. You feel the weight of your body. You feel the ground beneath your feet. You feel the firmness of every surface you touch. All of these sensations feel real and substantial and material. But the material reality behind those sensations is almost entirely empty space. The atoms that make you up are cathedrals of emptiness with tiny specks of staggering density at their centers. And those specks are themselves storms of energy, quarks and gluons in constant frantic motion, generating mass from the sheer intensity of the strong force. You are not made of solid stuff. You are made of forces and energy, arranged in patterns so precise and so stable that they create the illusion of solidity. The nucleus, That femtometer scale seed at the center of every atom is the densest, most energetic, most consequential structure in ordinary matter. Everything else, the electron cloud, the chemical bonds, the molecules, the materials, all of it is a consequence of what the nucleus is and what it does. Every atom in your right hand may have come from a different star than every atom in your left hand. The iron in your blood was forged in the core of a star that exploded before our solar system existed. The oxygen you just inhaled was fused from carbon in the interior of another long-dead star. The calcium in your bones, the phosphorus in your DNA, the trace amounts of copper and zinc and selenium that your body needs to function. Each of these nuclei was built through nuclear processes in stellar furnaces scattered across the galaxy over billions of years. You are assembled from the debris of dead stars, held together by the same forces that hold the nucleus together. The strong force that binds quarks into protons. The residual strong force that binds protons and neutrons into nuclei. The electromagnetic force that arranges electrons around those nuclei into atoms and bonds those atoms into molecules. Layer upon layer of force and structure, from femtometers to meters, from quarks to consciousness. The nucleus is where it all begins, not the beginning of the universe. That's the Big Bang, not the beginning of stars. That's gravitational collapse. But the beginning of substance, the beginning of mass, the beginning of identity for every atom that exists. The nucleus is the seed from which all material complexity grows. Without it, there is no matter as we know it. No elements, no chemistry, no planets, no life, no you. And it does all of this while being 100,000 times smaller than the atom it defines. Invisible, silent, hidden at the center of everything, building the world from a space too small to see. The next time you pick up something heavy, a book, a stone, a glass of water, think about what you're actually holding. Trillions upon trillions of nuclei, each one a femtometer scale knot of protons and neutrons. Each proton and neutron a furious storm of quarks and gluons, each one carrying mass that's almost entirely made of binding energy. You're holding energy. Energy given structure by the strong force. Energy locked into patterns so stable, they've lasted since the stars that forged them exploded billions of years ago. That's what the nucleus is. The smallest meaningful structure in matter. The densest object in ordinary nature. The engine of every star. The forge of every element. The source of almost all mass. And the foundation upon which every atom, every molecule, every cell, every living thing, every planet, every star, and every galaxy is built. All of it. From a speck you could never see. All of it. From something so small that calling it small barely captures the reality. The atomic nucleus. The tiny, dense, extraordinary heart of everything that exists. Thank you for joining me on this journey into the smallest and most consequential structures in the universe. If you found this exploration valuable, a like or subscribe helps more than you know. It keeps these deep dives into the nature of reality coming. And remember, you are walking through the world right now, carrying trillions upon trillions of atomic nuclei inside you. Each one forged in a star, each one holding almost all of your mass, each one a monument to the power of the strong force operating at scale smaller than anything you could ever see. You are made of stardust, held together by the strongest force in nature, built from specks so tiny they make atoms look like galaxies. And that is extraordinary. Good night. And may you never look at matter the same way again.